Paul Sutter is an astrophysicist at The Ohio State University and the chief scientist at COSI Science Center. Sutter is also host of Ask a Spaceman, We Don't Planet, and COSI Science Now. Sutter contributed this article to Space. Comms Expert Voices, Op-Ed and Insights. I think it's time for everyone to admit that black holes are annoying. Out there, drifting around the galaxy, with their much bigger cousins lurking in the centers of those galaxies, black holes are the ultimate paradoxes of nature, silently mocking our feeble attempts to understand them. By all accounts, black holes should not exist, and for a long time, they were shrugged off as mere mathematical artifacts, an annoying bug in the otherwise elegant machinery of general relativity. But then, there they are. A hole in the theory. The German physicist Karl Schwarzschild was the first to discover black holes. In 1915, he devised a solution for general relativity applicable to the simple non-rotating, uncharged, boring case of a perfectly spherical object embedded in otherwise empty space. While this sounds a tad idealized, the setup is close enough to real scenarios like our own solar system that it can be quite useful. I put discover in quotation marks because Schwarzschild didn't jump out of the trenches of the Eastern Front, where, while not solving fantastically complicated equations, he was fighting the Russians during World War I, exclaiming that he'd found a new astrophysical object. But buried in his mathematics were the hints of something darker. Those hints take the form of what we now call the Schwarzschild radius and the singularity. Every object has a Schwarzschild radius assigned to it, and that number is determined by the object's mass. Within this radius, the behavior of gravity starts to get a little weird. But that's fine, because in almost all cases, the radius is very small compared to the object itself, and rests far inside it. For example, our Sun is about 870,000 miles, 1.4 million kilometers, across, and it boasts a Schwarzschild radius of 9 miles, 3 kilometers. The fact that gravity behaves weirdly inside the Schwarzschild radius is nothing to sweat. For one, we really only care about the gravity outside the object, and two, we know other physical processes will take over and swamp any gravitational weirdness inside that radius. General relativity acts weirdest of all at the center of massive objects, a location called a singularity, where the equations developed by Schwarzschild to explain the nature of gravity simply blow up to infinity and aren't useful at all. But that's fine too, because it's just a math bug. It's not like anything in nature could actually get that small, right? Right? Into the dark. What if an object could be compressed so much, reaching such ridiculous densities, that its Schwarzschild radius were on the outside, instead of safely buried in the center, away from where its mathematics could cause any trouble? Well, that would be weird, because then there would be no other physical effects to swamp out the oddity of gravity at this boundary. Indeed, gravity would be so strong at this boundary that nothing, not even light, could escape. And any matter that fell in would spiral helplessly to its doom in the infinitely dense singularity. If such an object existed, then the singularity and the Schwarzschild radius would be promoted from mathematical craft to physical object. Spoiler alert. It's a black hole. For decades, it was assumed that something, anything, would prevent stars from forming black holes. But after the discoveries of white dwarf stars and neutron stars, both immensely dense, and the first hints of the triggering mechanism for supernovas, black holes began to take hold as a concept. As much as they ought not to exist, if they did exist, they would have certain real observable testable properties. So at least science can do its thing, discard this crazy notion and move on with its life. And oh boy, did the evidence start to come in. A massive dying star, orbiting an unseen companion, that pulls on its atmosphere so much it emits powerful X-rays. Stars in the center of the Milky Way orbiting a massive, hidden object. Powerful radio sources emanating from active galaxies, with energies only reached through immense gravity coupled to fantastic rotation. And most recently, the subtle whisper of gravitational waves sloshing over the Earth. The inescapable conclusion. Black holes are real. A singular problem. We've come to terms with the event horizon, the name now given to an exposed Schwarzschild child radius. The nature of space-time inside that boundary does indeed get all sorts of funky, but hey, nature does lots of funky things, so after a few decades of mulling it over, scientists decided it wasn't so bad. But the singularity remains, the point of infinite density at the center of every black hole. That word, infinite, is a hard pill to swallow. When infinites appear in the mathematics, it's a signpost that we're doing something wrong, that our machinery isn't quite up to the task. We're missing something. No matter what, we can't point to any other force or effect or pressure to stop the catastrophic collapse of matter into a singularity, and we've really tried hard. But we know our theoretical models, i.e., general relativity, are incomplete. There isn't really a singularity at the center of a black hole. But we simply don't understand strong gravity at small scales. That's the domain of a full-on quantum theory of gravity, which we haven't cracked despite decades of trying. Hard. So the question of whether black holes exist comes down to your definition of the word exist. Quote, black holes as astrophysical objects. Yeah, it looks like nature can manufacture event horizons just fine. Black holes is a 100% complete picture of the way nature works. Those certainly don't exist, and will eventually be replaced by a more accurate picture.